Welcome back to the deep dive. Today we are tackling a subject that, on the surface, feels, it feels completely settled. It
Right.
feels like something you learn in kindergarten and then, never think about again.
You talk about the shape of the Earth.
I am. And look, I know what you're probably thinking. Why are we doing a deep dive on this? Just show me a picture from the ISS.
Mhm.
But as we started digging into the source stack, and it's a wild stack today, from ancient Greek philosophy to Reddit threads and some incredibly dense papers on general relativity, we realized something.
You realize that knowing the Earth is round and actually proving it are two very, very different things.
Exactly. Or, well, not just proving it, but understanding how we figured it out. Because for most of human history, we didn't have satellites.
Nope. No NASA. We had sticks. We had wells. We had really, really long walks. And yet, thousands of years ago, people figured this out with just shocking precision.
So that's the mission today. We are not here to dunk on conspiracy theorists.
No.
We're here to sort of celebrate human ingenuity. We want to walk through the evidence from the stuff you can literally see at the beach all the way to some mind-bending physics with Einstein and warped space-time.
From a simple boat to the geodesy of gravitational waves.
Let's start with the view from the ground, the most basic, I can see it with my own eyes, evidence.
Okay.
The stack brought up a classic analogy from popular science they call the ant and the orange.
This is a great place to start because it's all about scale. So imagine you're holding an orange,
Right,
and there's a tiny ant walking toward you on its surface.
right.
Because that surface is curved, you don't see the whole ant all at once.
You'd see the antenna first, then his head kind of pops up, then the legs, and finally the whole body comes over the horizon of the fruit.
Exactly. Now contrast that with an ant walking down, say, a long flat road toward you.
It wouldn't rise up.
No, it would just materialize. It starts as a tiny dot and gets bigger, but you see the whole thing the entire time.
And this isn't just about ants and oranges. We see this in the real world with ships. This was one of Aristotle's big observations, 350 BCE?
It was. He spent a lot of time watching ships in the harbor. And he noticed that when a ship sails away, it doesn't just shrink into a dot.
The hull goes first.
The bottom part, the hull, disappears first. Then the sails, or on a modern ship, the bridge and the radar masts.
Yeah.
They're the last things you see. It literally looks like the ship is sinking.
Okay, but I have to play devil's advocate here for a second because this is where the counter-arguments start.
Sure.
Couldn't that just be perspective? The ship is just getting so small that my eye loses the detail of the hull first.
That's a fair question.
Eh.
But here's the test. Get a pair of binoculars or a telescope.
Okay.
If the Earth were flat and the ship was just small, zooming in would bring the whole thing back into view. You'd see the hull again sitting on the water.
But you don't.
You don't. Even with a powerful telescope, that hull is gone. It is physically blocked by a wall of water. The curve of the Earth has risen up between you and the boat. You cannot zoom past the curvature.
Speaking of curvature, the sunset, there was this fascinating bit in the notes about the Burj Khalifa in Dubai.
Ah, yes. The double sunset. This is a classic cocktail party fact, but it's actually deep physics.
So the setup is this. You're on the ground floor, you watch the sun dip below the horizon, it's gone.
Right. Your line of sight is blocked by the curve of the Earth.
But then you sprint to the elevator, which in the Burj Khalifa travels at 10 meters a second, and you shoot up to the observation deck,
And suddenly you can see over the curve again.
and you watch the sunset a second time.
You do. Which should be impossible on a flat plane.
Right.
If the Earth were flat, the sun would just be moving away from you. It would get smaller and dimmer, but it wouldn't set below anything. Being higher up wouldn't just make it reappear. The only reason height buys you more daylight is because you are looking around a ball.
Most of us don't have access to the Burj Khalifa, but I saw a suggestion for doing this at the beach.
Yes, the core man's version. You lie down on your stomach on the sand, watch the sun set until the very last sliver is gone.
Okay.
Then stand up as fast as you can.
You actually catch it again.
You catch just a tiny glimpse of it setting again. Your eyes moved up 5 or 6 feet, which shifted your horizon just enough to let you peek over the curve one last time.
Or I saw in the Reddit thread, you could use a drone, fly it straight up right after sunset, and the camera sees the sun pop back up.
Works perfectly. But before we move on, I have to add a caveat. Because nature loves to mess with us.
Uh-oh.
We have to talk about the Chicago skyline problem.
Oh, right. I've seen these photos. Someone is on the shore of Lake Michigan, and they can see the Chicago skyline, but the math says it should be hidden behind the curve.
This is where people get tripped up. They say, the curve is a lie. But what they're seeing is atmospheric refraction.
Okay, break that down. Is the atmosphere acting like a lens?
Precisely. The air near the water is often colder, and the air above it is warmer. That density difference literally bends light rays. It bends them around the curve of the Earth.
So we are literally seeing around a corner.
In a sense, yes, it's a mirage. And the giveaway is that the image is usually distorted, it's shimmering or stretched, or sometimes even upside down. It's an optical illusion, not reality.
So visual evidence is strong, but our eyes can be tricked. Let's move to something a bit more solid. Let's look up.
The celestial evidence. This is historically how we really nailed it.
And we're back to Aristotle again. The man was observant. He was looking at lunar eclipses.
Right. A lunar eclipse is just the Earth passing between the sun and the moon.
So that shadow on the moon is our shadow.
It's the Earth's shadow. And Aristotle noticed that no matter when the eclipse happened or where the moon was, the edge of the shadow was always a perfect curve, a perfect arc.
And why does that prove it's a sphere? Couldn't say a flat disk cast a round shadow.
It could, but, and this is the key, only from one specific angle. If you hold a dinner plate face on to a light, you get a circle. But what if you tilt it?
You get an oval, or just the thin line if it's edge on.
Exactly. And since the Earth is spinning and orbiting, we see eclipses from all sorts of different angles relative to the sun. But the shadow is always round. The only shape that casts a circular shadow from every single direction is a sphere.
That makes perfect sense. But the one that really clicked for me was the stars.
The ancient GPS.
Right. Aristotle pointed out that stars you could see in Egypt were just gone when you went north.
Let's visualize this. Say you're at the North Pole. The North Star, Polaris, is directly overhead, straight up.
90 degrees.
Right. But as you travel south, say you fly to Miami, Polaris, sinks lower toward the horizon.
And if I keep going south to Brazil,
It drops below the horizon entirely. It's gone. And suddenly you start seeing new stars, like the Southern Cross that no one in the Northern Hemisphere ever gets to see.
which just doesn't work on a flat map.
No way. If the Earth were flat, everyone would be looking at the same star dome. Polaris might get dimmer if you were far away, but it wouldn't physically drop below a horizon and be replaced by new constellations.
There was a great detail from Reddit on this about the moon, the upside-down moon.
This is a fun one. If you call a friend in Australia while you're in the US and you both look at the moon, the man in the moon face is oriented differently for each of you.
Wait, really? Upside down?
To the person in the southern hemisphere, yes, the moon appears upside down relative to how you see it.
Wow.
It's a geometric necessity. You are literally standing upside down relative to each other on the surface of a ball. There is no way to replicate that on a flat plane where everyone is standing up the same direction.
Okay, we can't do this deep dive without talking about Eratosthenes, the stick test.
Oh, this is the best story. 240 BCE. He's the head of the Library of Alexandria.
The internet of the ancient world.
Basically. And he reads a report from a town called Syene, which is modern-day Aswan. It says that on the summer solstice, at high noon, the sun shines directly down a deep well without casting a shadow.
Meaning the sun is directly overhead, 90 degrees.
Exactly. But Eratosthenes is in Alexandria, hundreds of miles north. And he knows that at that exact same time, a vertical pole in his city does cast a shadow.
So right away, he knows the Earth must be curved.
He does. Because if the sun's rays are all coming in parallel, a flat Earth would mean no shadow anywhere. But he has one.
So he measures the angle. It's 7.2 degrees.
Which is about 150th of a full 360-degree circle. So the logic is simple. If the angle difference is 150th of the circle, then the distance between the two cities must be 150th of the Earth's circumference.
Okay, but this is the part that blew my mind. How did he know the distance from Alexandria to Syene? There's no Google Maps?
He had to hire people, professional walkers.
Professional walkers.
Yes. Their entire job was to walk between cities with perfectly consistent steps to measure distance. So Eratosthenes pays these guys to walk across the desert, counting their steps. They came back with a number, roughly 5,000 stadia.
So he takes 5,000, multiplies by 50.
And gets 250,000 stadia. And depending on which stadian length you use, his calculation for the circumference of the Earth comes out to around 40,000 kilometers.
Which is what?
Which is within about 1 or 2% of the value we use today.
That's just absurd. A guy with a stick and some paid walkers figured out the size of the entire planet 2,200 years ago.
Geometry and logic, that's all you need.
So we have shadows, stars, and walkers. But let's talk about what we can feel. Let's talk physics. Let's talk gravity.
Ah, gravity. Gravity is the engine of the sphere. It pulls everything toward the center of mass, which is why planets form into spheres in the first place.
So standing here, down is always toward the center of the Earth.
Right. Whether you're in London or Sydney, down is just beneath your feet.
But on a flat Earth model, a disk,
Right.
the center of mass would be the middle of the disk, right? Like the North Pole.
Exactly. So if you're standing there, gravity pulls straight down,
Yeah.
normal, but start walking south toward the edge.
Gravity's still pulling toward the center, which is now behind me.
Yes. So as you walk outward, gravity starts pulling you diagonally. It would feel like you're walking up an increasingly steep hill.
So by the time I get to the edge,
Gravity would be pulling you almost horizontally. You'd have to crawl. Trees would grow sideways. The fact that an apple in Australia falls straight down proves that mass is distributed spherically under your feet.
that's a terrifying image. Sideways gravity. Okay, let's talk rotation. The Foucault pendulum.
Oh, I love the Foucault pendulum.
Yeah.
It's not just proof of shape, it's proof of motion.
So paint the picture for us. What is it?
Imagine a huge, heavy pendulum on a very long wire swinging back and forth. Newton's laws tell us that a pendulum wants to keep swinging in the same plane forever.
Okay, so if I set it swinging north-south, it just stays north-south.
Ideally. Now, put yourself at the North Pole, you set up this pendulum, the Earth is spinning under you like a turntable.
But I'm standing on the turntable, so to me...
Right. To you, it looks like the pendulum is slowly rotating. In reality, the pendulum is fixed, and you are the one rotating around it.
Okay, that makes sense. At the pole, it would do a full 360-degree rotation in 24 hours.
Precisely. But here's where the geometry gets cool. Move that pendulum to the equator.
Okay.
At the equator, the ground isn't twisting underneath the pendulum, it's just moving sideways. The pendulum's swing plane and the Earth's rotation are aligned.
So it doesn't rotate at all?
Not at all. The time it takes is infinite.
And what about in between? Like Paris?
This is the magic. There's a formula. The rotation time is 24 hours divided by the sine of your latitude.
Okay.
In Paris, the math predicts it should take about 32 hours to complete a circle. And when they hung the famous pendulum there,
It took 32 hours.
exactly 32 hours. It's a direct, physical measurement of the Earth's spherical geometry and its rotation. You can't fake the sine of your latitude.
That is incredibly cool. But I feel a but coming.
There's always a but. We've been saying sphere this whole time.
Then it's not a perfect sphere.
It's an oblate spheroid. Because it spins, it bulges at the equator. It's about 21 kilometers wider than it is tall. It's squashed. And some data even suggests it's slightly pear-shaped.
Okay, a squashed, lumpy ball. I can handle that.
Wow.
But then we read this paper from Mark Sivif, Geoids in General Relativity, and the vocabulary got very scary.
He was a bit dense.
Geoid, quasi-local frames, shearing flux. Can you translate this? Why does Einstein care about the shape of the Earth?
Okay, so normally we define the shape of the Earth by sea level, which we call the geoid. In simple Newtonian physics, that's just a surface where gravity pulls with equal strength.
Right, water finds its level.
But Einstein says gravity isn't a force, it's a warping of space-time.
Here we go.
Think of it this way. Newtonian gravity is like a vacuum cleaner sucking you down. General relativity says the Earth is a heavy ball on a waterbed. It creates a dent. But because the Earth is spinning and squashed, it's not just making a dent, it's twisting the fabric of the waterbed. Yes. The paper talks about shearing. In this context, it means the gravitational field itself has a twist to it because of the Earth's bulge, its quadrupole moment.
So if we only use Newton's math, we're missing the twist.
We're missing the twist. The paper argues that to define the Earth's true shape with absolute perfection, you have to measure that shear. You have to account for how the Earth is literally dragging space-time around with it.
So the Earth isn't just a round rock. It's a lumpy, spinning mass that is physically dragging the fabric of the universe along for the ride.
That is the expert flex. We're not just round.
Yeah.
We're dynamically warping reality, and our GPS systems have to account for that to be accurate.
Wow. That puts the ant and the orange into perspective.
Mm.
Okay, before we wrap up, I want to bring this back down to earth, the Reddit thread about the Adelaide problem.
Yes, this is a great little logic puzzle.
So a listener is in Adelaide, Australia. It's December, their summer. And they notice the sun rises in the southeast and sets in the southwest.
Okay. Now, try to map that on a flat Earth model. The North Pole is in the center, Antarctica is an ice wall around the edge.
Got it. Australia is kind of on the outer part of the pizza.
Right. So if you're in Australia and you look southeast or southwest, where are you looking?
Toward the edge. out toward the ice wall.
Exactly. So for the sun to rise and set out there, it would have to be circling way out beyond Australia, near the edge of the world.
It would have to, like, swerve way off its normal path, do a big loop, and then come back in.
It would need to perform impossible acrobatics.
Mm-hmm.
But on a globe, it's simple.
It's just the tilt.
It's just the tilt. The southern hemisphere is tilted toward the sun. The sun's path appears further south. You don't need magic physics. You just need a ball.
It all comes back to consistency. The globe model explains the ship, the eclipse, the pendulum, the gravity, and the Australian sunrise with one single elegant system.
You don't need a separate excuse for every single phenomenon. It all just fits.
So for the listeners who want to prove this themselves, you mentioned the sunset trick.
The sunset trick is the best and easiest. Or, if you're feeling ambitious, rent a surveyor's tool called a theodolite. Go to 2 different hills and measure the angle to the horizon. You'll find it's always below eye level. On a flat plane, it should always rise to meet your eye.
So what does all of this actually mean for us? Why does it matter that we get the shearing of space-time or the shadow on the moon?
I think it matters because it reminds us of our place. We are these tiny creatures on a massive, complex object. But more than that, it reminds us of what we're capable of. We figured all this out without leaving the ground.
And as that general relativity paper showed, we aren't even done.
We're never done.
Yeah.
Round was the first answer. Oblate spheroid was the second. Geoid quasi-local frame with shearing flux is the current one. Science isn't about memorizing a fact. It's about constantly sharpening our understanding of reality.
That is a thought to chew on. So tonight, go watch the sunset, and when it disappears, stand up fast. See if you can catch the world turning.
Just try not to trip in the sand.
Thanks for listening to The Deep Dive. We'll catch you next time.